All right, here is mini lesson for writing equations for exponential growth or decay. Now this is only that first skill, this is not compound interest yet. So the general equation that we're going to be working with is y equals ab to the x, where a is going to be the initial amount that you're given to work with, and b is going to be your growth or your decay factor depending on the problem. Now, what's really important here is that when b is greater than 1, you're dealing with an exponential growth equation, because when we take a number that's bigger than 1 to an exponent, it continues to grow. If you're dealing with exponential decay, then you're actually going to have a decay factor, so your b value is going to be less than 1, because when you repeatedly take that to an exponent, your value is going to get smaller. So, taking a look at this first problem, we have wildlife manager determines that there are approximately 200 deer in a certain state park. So right away that's jumping out to me as the initial amount. So A is 200. Now the population is growing at a rate of 7% per year. How many deer will be in the park after 4 years? So this is the most important piece. Whoops. We need to write this as a growth factor. So we know that this number needs to be bigger than 1. And so what we do is we think about 7% not as a percentage, but as a decimal 0.07. So your growth factor is going to be 1.07. Because if you're growing at 7% per year and you already have 200 deer, we need to add 7% to that. So this is going to ensure that we have a growth equation. And then in this part, in letter A, we want to know what's happening after 4 years. So x is going to be equal to 4 years. So our general equation is going to be y equals 200 times, 1.07 to the x power. But in this problem, we want to know what happens after 4 years. So y is going to be equal to 200 times 1.07 to the 4th power. Okay? So I'm going to put that in my calculator. You can't see this happening, but hopefully you'd end up at the same place. I'm going to take 1.07 to the 4th power, which gives me 1.310 and some change. Then I'm going to multiply that by 200. Hopefully you're doing this in your calculator as well. So after 4 years, y is going to be equal to 262. We'll round it to 1/6 deer. Obviously, you can't have 0.16 of a deer, so we could round up. Now, in letter B, it says if the carrying capacity of this park is 350 deer. So it's a y value, because y is standing for the number of deer. We want to know how long it's going to take for the deer population to reach carrying capacity. Now, that's going to give us a y value, and so the easiest way to solve this is to go into Desmos, which I have lost altogether. Sorry about this, guys. I'm still new. And what we're going to do is we're going to graph the 1.07. We're also going to graph y equals 350. And using Desmos, we can see where they intersect. So I'm going to pull up Desmos. We're going to pull up these two graphs, and we're going to see where they intersect. All right, so what you see here is I've graphed the line y equals 350 because that's how many deer we have, or that's the carrying capacity. And I've also graphed 200 times 1.07 to the x. So what we can do is we're going to zoom in, and where those two lines intersect is going to tell us the number of years we have until this happens. So it looks like our point of intersection is 8.271, 350. So that means that we're going to hit that carrying capacity of 350 deer in 8.27 or 8.3 years. So when you're asked to solve that equation, the easiest thing to do is to go into Desmos and to graph it. So then now that we're back here, we know that this is going to happen after, in letter B, this is going to happen, let's find my cursor, in 8.27 years. So there's an exponential growth problem. In this case, we've got, in the next problem, I want to show you an exponential decay problem. So a business purchases a computer system for $3,000. Well, that jumps out to me as the initial value of $3,000. And the value of the system is going to decrease at a rate of 15% per year. Well, 15% as a decimal is 0.85. Okay? Remember I said that B is our growth or our decay factor. In this case, we're decreasing. That means it needs to be a decay factor. So if something is losing a value of 15% per year, that means it's retaining a value of 85%. So I just found that by taking 1 minus the 15%. So our decay factor here is 0.85, and that's going to guarantee that the value of this is going to decrease 15% per year, or each year hold 85% of its value. And so then it wants us to know what's going to happen after 4 years. So that's going to be the x that we end up plugging in. So our general equation is going to be y equals 3,000 times 0.85 to the x power. Now x is equal to 4, so that means y is equal to 3,000 times 0.85 to the 4th power. We're going to get out our handy-dandy calculators and make sure we're at the same place. So hopefully you're doing this along with me. So I have 0.85 to the 4th power, 0.85 to the 4th, which gives me 0.522, and I'm going to multiply that by 3,000. And that gives me a value of $1,566, and if we round it, 2 cents. So after 4 years, this computer system is going to be worth $1,566.02. All right, that's exponential growth and decay.